So if you want to go back, you do it like that.
The button doesn't work.
Oh, sorry, like that is to go back.
Yeah.
Yeah, yeah.
So
Okay.
yeah. And if you just, I'm sorry, it's like that is to go to
Or
forward
just,
and yeah.
Back.
If you need to go somewhere in a specific place, you just go there and like page 9, for example, and it will be like.
Okay, thank you. Maybe I will look at there's a page with a lot of.
No, you need to tap at somewhere at the center. If you,
No,
Yeah.
no. Actually, the tab will go to this.
it depends on where you tap. So if you tap at the center, it shows this panel, and at the right, it goes forward.
Yeah. Let's see, there is a page.
Oh, you found out how to solve the slides problem.
Okay, it's almost.
Android.
Yeah, thank you.
So if you tap there, you will go
Oh, great.
to this page,
Also,
and if there, you will.
Yeah.
So you can.
And if you
either
tap
swipe
center,
or-
you get that
or
panel.
tap.
You can swipe as well. Can I try to swipe?
yeah, here.
Swipe the
Yeah, swipe as
or
well. It works.
in that direction it will give
Great.
他用了一个新的软件，刚才是 WPS 是我们中国的软件，然后现在用的，
他这里面有来FPS，
对，
真的。
对他刚才是和郭帅找到，他现在是他用了另外一个，
WPS 放那个撇点，
对他放不了 P。
Okay, let's start. The next talk today is Ji Yang. He will talk about mapping partition functions and the mapping universally conjectures. Please.
Thank you very much. It's a great pleasure to come here, and first I would like to thank the organizers for the invitation. So today I will talk about a recent joint work with Don's idea about some deformation of KDV hierarchy. So and also some axiomatic way to inter-systems. So yeah. So first let's recall the famous KDV equation and KDV hierarchy. So the KDV equation was discovered in the study of shallow water waves in 19th century by Smith and Kotovich de Vries. So nowadays it is well known that this nonlinear partial differential equation can be extended to a family of pairwise commuting evolution PDEs called the KDV hierarchy. So this hierarchy has this form. So they have infinite many equations, and always start with this u to the power I divided by I factorial ux, and plus some other terms. And since this system is pairwise commuting, so we can solve this infinite many PDEs together, and so solutions will depend on infinite many variables t. So this t is the infinite vector of indeterminates. So t0 is x and t1 is t. Is this original time? And so when epsilon equals 0, this KDV hierarchy is also called the dispersionless KDV hierarchy, and also called Riemann-Hopf hierarchy. So yeah. So in 1990, Witten made a famous conjecture. So he actually in Professor Liu and Professor Fan and also Borshai's talk, we already see some of the terminology, so it's make it easier. Witten's conjecture says the partition function of psi class integrals on the Deligne-Manford moduli space of stable curves is a particular tau function for the KDV hierarchy. So in particular, if we define U to be the second derivative of log tau, log Z, then this U satisfies the previously infinite equations, satisfy the KDV hierarchy. Okay, so here the partition function is a generating series of all these psi class integrals. So psi is the first term class of the tautological line bundle on the moduli space of curves. And Witten's conjecture was first proved by Kontsevich and is now also well known as the Witten-Kontsevich theorem. Mirzakhani, Kazarian, Randall, Chen Liu, Okenkov, Pan, and many and several other groups gave different proofs of the Witten-Kontsevich theorem. So now let's start from some new terminology. So first of all, we will fix a ground ring R. It essentially can be any ring, and let this G to be the this invertible power series of one variable, the set of all invertible power series of one variable, starting with the identity. So this group, of course, is very famous. So the group law will be given by composition. So this group is very famous already, dates back to Riemann, because we want to study conformal maps, and we have Riemann's theorem. And so it's a very famous group. So we will define a affine linear right action of this group on infinite tuples T, on the infinite many times. So how do we define it? So after the right action, little t will become capital T. And this T and T are related by this relation. So this relation,
What is phi?
phi is the group element. So, sorry, for any phi in G, any phi in G.
Not phi, yeah.
Phi is any group element in G. So for any group element phi, we define this map. And to see it is a right action, the simplest way is that we take square on both sides of this defining equation. We get on the left hand side b capital T square equals phi prime times b little t square, and then we multiply both sides by dv, the one form dv, d capital V, and then this phi prime v dv will become d phi, right? So it becomes an equality defining equation of one form, using one form. And then from this one form, we can read that if we make composition, if phi is given by phi, if phi is given by phi 2, composite phi 1, and then we can see this definition is indeed a right group action. Okay. Explicitly, let's write this arbitrary group element phi as the sum ak v to the power k, and a0 is 0, a1 is 1 because it's starting from identity. So and all the other a2, a3, and so on is there's parameters for this infinite non-abelian group. And so if we just substitute this phi to this definition, we can write down this definition more explicitly. So you can see the first few capital T. It's just, for example, T0 is little t0, T1 is little t1 plus A2 T0, and capital T2 is little t2 plus these terms. And also a group action is not, so here we also have since it is a group, also each element has an inverse. So here we can also get the inverse map. So So it's a triangular map. It's affine linear. So most is linear, but here there is a shift. So it's affine linear map. So this group action is different from those of given tools or Chateau's, because here the group law is given by composition. So it's very different from usual given to or Chateau group. The group law is given by multiplication. So this definition was motivated from a work of Sasha Alexandrov for a special group element when this phi equals e to the 2qb minus 1 divided by 2q. Okay, so later we will see Alexandrov's example. So, okay, so now let us denote by log
But
z.
anyway, it's still triangular, yeah?
Specifically,
The replacement is triangular.
it's triangular. Yes, it's invertible. It's triangular invertible. Yes. So it's It's all. When it goes on, you can compute this triangle, infinite triangle. So the series of the partition function we take log, we call it free energy, and denoted by f. So our first, our second definition is we define the WK mapping partition function associated to any group element phi to be the action of this phi inverse on the Witten-Kontsevich partition function. Similarly, the action on the free energy is also defined as this red action. So it means from one partition function, which is the famous Witten-Kontsevich partition function, we immediately obtain new partition functions. This partition function depends on infinite parameters phi. Yeah, it's encoded in phi. Okay, so yeah, so by definition, this mapping partition function has a Born genus expansion because our Witten-Kontsevich free energy has a genus expansion. So by definition, our mapping partition function is also has this genus expansion, and each genus G free energy is also defined by the genus G Witten-Kontsevich free energy by this right group action. So it's the definition is very simple. Okay, and in genus 0, so our first definition result is about genus 0. In genus 0, our result says this genus 0 partition free energy is G invariant. So you have a huge group action, but actually when you act, it does not change the genus 0 free energy. So it also means the Witten-Kontsevich free energy in genus 0 and possibly for any conwritten free energy in genus 0 has some large group action to make it invariant. So in particular, we can write this result as this F0 phi, the genus 0 mapping free energy equals or as a function equals the Witten-Kontsevich free energy in genus 0. So let's give the proof. So first we introduce this very famous power series explicitly. Equivalently, this power series can be defined as the unique solution to the Riemann-Hopf hierarchy with the initial data E at time higher times equals 0 equals x. Okay, so for this initial data, you get this, the solution is this famous power series. And this famous power series satisfies this Riemann-Hopf hierarchy. Okay, so by elementary exercise, we can prove that for any group element, this phi acting on this famous power series makes this E from capital T equals this E little t. So it's elementary, but of course it's also very interesting. So here capital T and little t are related by that group action. And also if we take the first derivative of E capital T with respect to little t, we get this, it satisfies this equation. So it's actually here that there's some the derivation here is very similar to Professor Liu's talk. Here you have some vector field on the big space. And also we know that the genus zero Witten-Kontsevich free energy has satisfied these identities. So the second derivatives of F0WK equals to powers of E. And using these three equations, this one, we can prove that after the group, the right group action, the second derivatives of this series does not change. And then we apply the genus zero Delatte equation, we can prove the whole power series is invariant, is G invariant. So this proves the theorem. So the theorem says this genus zero Witten-Kontsevich free energy is invariant under this group action. Okay, so what about higher genus? So for higher genus, it is known that the power series FGWK for G bigger than or equal to 1 can be written as, it's an infinite series, can be written as a function of finite number variables. And this is similar to Shuaibo's previous talk. And here we used this, it can depend on 3G minus 2 functions, which are derivatives of this famous series ET. Okay, so this is called the jet representation in systems. And this jet representation dates back to digraph Witten, Itsuksen Tsuber, and Yaguchi and his collaborators, and Dubrovin Zhang. Okay, so in this representation, the Witten-Kontsevich free energy, for example, in genus 1, this F1WK is just 1/24 log V1. Okay, and in general, it's a polynomial of V2 to V3G minus 2 and a rational function of V1. And also it satisfies certain homogeneity equations. Okay, so these are quite standard. Okay, now we substitute the group action, because in the group action, you see, in the group action here, the fundamental this famous series we denoted by ET because it's like very fundamental element. It's like the building blocks. So this ET under the group action changed in this way. And if we use this equation iteratively, we take successfully derivatives with respect to T0, we will get a map between derivatives of capital T0 and the derivatives of little t0. And then we substitute this map to this jet representation, we will get this proposition. This proposition says genus G, mapping free energy, also has jet representation. In particular, F1 phi, you see, now it becomes 1/24 log V capital V1 plus a new term. This term is what was not in Witten-Kontsevich free energy. This term is because of the group action. So there are some new terms come from the group action. When this group element is the identity element, which is phi v equals v, in this case, phi prime is 1, so we get 0. Okay, so this extra term of the group action vanish when phi equals identity. Okay, and in general, our FG phi is also can be represented as a polynomial of this E capital T and its derivatives. And the rational function of the first derivative of et. Okay, and also it satisfies certain homogeneity condition. So this proposition is just obtained by definition. Okay, and yeah. So let's look at, for example, g equals 2. When g equals, so previously we already look at g equals 1 is this, and when g equals 2 it is the same. So the first three terms was in original genus 2 Witten-Kontsevich free energy, and all this second line and third line, all these terms are new terms. And this term, again, they must vanish when phi equals identity. So when phi v equals v, you see here's second derivative, third, and all this disappear, and all this disappear. So when phi is identity, this f2 goes back to original Witten-Kontsevich genus 2 free energy. So in general, we make a generating series of all higher genus free energies, or these mapping free energies, and then we can, by using Virasoro constraints, we prove with Zagir this theorem. So the theorem says this generating series of higher genus, all higher genus mapping free energies satisfy the Dubrovin-Zhang type loop equation. So this generating series, this one, satisfy this linear equation. And here, in this linear equation, we have certain generating kernels. So this W goes back to the Witten-Kontsevich case when phi equals identity. So you see, if phi equals identity, all this becomes very simple. Only one term survives is when s equals 0. So when s equals 0, there's only one term. So in that, that is the original Dubrovin-Zhang loop equation for Witten-Kontsevich free energy. And this loop equation has a unique solution up to a sequence of additive constants. And all these additive constants, pure constants, can be fixed by using the Latin equation. So then it means one can use this loop equation to uniquely solve all the higher genus mapping free energies.
So this loop equations are obtained from Virasoro?
Yes, from Virasoro, yes. Because we have this group action, you can substitute this group action in the Virasoro constraints, and you get Virasoro constraints for the mapping partition function. And then you use Dubrovin-Zhang formalism, it's just the same, and you get this equation is generalized. So now since we have now the description for the free energies, so we will consider integrable hierarchy. So what we do is to use again Dubrovin-Zhang's formalism. So in Dubrovin-Zhang's formalism, we know a general notion is that partition function would be some tau function of certain integral systems. In particular, Dubrovin and Zhang starts from any cohomology field, semi-simple cohomology field theory, from any partition function of this cohomology field theory, they construct an integral system. So now the situation is again very similar, because we have a new partition function. It's a partition function depending on even many parameters encoded in this group element phi. So then we use Dubrovin-Zhang's formalism. Consider the second derivative of log z phi with respect to capital X. Capital X is T0. And this definition of U phi gives rise to a so-called Cauchy-Murray transformation. It's Cauchy-Murray because here the difference is that in Cauchy-Murray we consider capital at Fg, so those rational functions. And instead of this infinite series, we substitute this Fg phi to be this capital Fg. So capital Fg are just these functions. Okay, so it's a finite number of variables, and then we substitute this Cauchy-Meurer transformation into this Riemann-Hopf hierarchy. So here we call it local because in the Riemann-Hopf hierarchy is an infinite family, but now we want more family. We want the times. It's not just those tk. We also the time are parameterized by an arbitrary function. It's again, it's very similar to Professor Liu's talk because it's in the big phase space we have actually more vector fields, and so for any smooth function S, the Riemann-Hopf hierarchy is like this. So du or dv or dv dt of S equals SV Vx. So when this S equals v to the power I divided by I factorial, those polynomial function, you will get the original Riemann-Hopf hierarchy. But here we want S to be any smooth function. In this case, we call it local Riemann-Hopf hierarchy. So when you substitute this Cauchy-Meurer transformation into the local Riemann-Hopf hierarchy, you will get a deformation of the local Riemann-Hopf hierarchy. And you see, this is the term appeared here, and all the other terms are deformation of this original Riemann-Hopf hierarchy. And when phi equals identity, so here, when phi equals identity, this disappear, this disappear, this disappear, and only this term and this term. In this case, this is the KdV hierarchy. So this equation is also a deformation of the KdV hierarchy. So when we have this hierarchy, we want to know what are they. So how to understand it from inverse systems. So our study will be quite inverse system. So we want to know what is this inverse hierarchy. Okay. So here I write down more explicitly more terms because here we only we truncate to epsilon 2, but here we gave also epsilon 4, and from this case, so here is T1. T1 is the original case when S equals V. So it's dV dt equals VDX. So in this case, this is just the flow of the KdV, original KdV flow, but we have a deformation group element phi. So when phi equals identity, now it's more clear. When phi equals identity, this disappear, and all epsilon 4 terms, all this disappear. Only one term survive is original KdV equation, U3 over 12. So now this gives a deformation of the KdV equation. Okay, and here you see there are many coefficients, and if we take logarithmic derivatives of phi prime, we can give a more elegant form for this equation, because here you have this convention, here you have this combination, and here, but if you take Lk equals logarithm derivatives of phi prime, and then you see this deformed KdV equation becomes, all the coefficients here becomes positive. And and it's clear when this phi equals identity, this disappears, just the KdV equation. Okay. Yeah. Anyway, so this positivity suggests maybe each coefficient of this hierarchy may also have some topological, direct topological meaning. Okay. So our next result says actually the WK mapping hierarchy has polynomiality. So this is from the first few terms to epsilon 4. Indeed, you see everything is polynomial. So polynomial means there's no denominators of U1, because in this free energy, each free energy there is denominator. There's V1. So when you do a Cauchy-Meurer substitution, here when you do cosimilar substitution, this map also has many denominators. But after you substitute to the Riemann-Hopf equation, here you see there's no denominators of U1. This is very non-trivial, and so we can prove it is indeed has polynomiality. So how do we prove it? Let's first show that for the KdV case, it is indeed has this polynomiality. Of course, for KdV, it is incosystems is well known. But since we have all the smooth function, the times are labeled by any smooth function, so we can give a little bit more proof. So it means for any smooth function, the KdV hierarchy has this polynomiality. You see, there's no denominators. Okay, so I will skip this proof. Moreover, there is a tau structure behind the KdV hierarchy. So if you substitute this, the tau structure in gender 0 is just the integral of S1 times S2, S1, S2 to be any smooth function. And the claim is that if you substitute the cosimilar transformation in the tau structure, it is also always polynomial. So this is known for S1, S2 are these polynomials, but it's maybe not very well known for any smooth function. But anyway, so this is for the case when phi equals identity, more or less it's standard. So we will actually give a proof based on this standard result later, because we will look at a more general situation. But here we first gave a more stronger result. So this result says, this result will say the deformed hierarchy is not just the integral system, it's not just polynomial, but also it is bihamiltonian. So let us define two operators as substitution in this hydrodynamic type Hamiltonian operators. So this is the hydrodynamic type Hamiltonian operator, and this compositions is essentially just coordinate how a bivector change when coordinate change. So we have we consider these two particular Hamiltonian operators, and since this hydrodynamic this part is the shortened brackets between P1, P2, P1, P2, and P2, P2 are always 0. It's standard dates back to Novikov, Dubrovin, and after coordinate change, of course, it still satisfies this vanishing of this shortened brackets, and but the bihamiltonian means it's not just this shortened brackets vanish, but also we need this bihamiltonian, this presume that these Hamiltonian operators to have polynomiality. This is again quite non-trivial. Okay, so this is the hierarchy by using written in terms in the bihamiltonian form. Okay, and so indeed the theorem says this bihamiltonian structure for the deformed hierarchy also has polynomiality. So it's a bihamiltonian integral system. How do we prove it? We consider this spatial variable capital X. We can see that partial dx is a linear combination of original times. Okay, and then by using the group action by an elementary exercise, you can see that this dx is which flow is the flow characterized by the particular smooth function, which is phi prime phi inverse u. So here for any smooth function we have a flow. So here this capital Dx flow is particular this flow, and we already proved for the KdV hierarchy this flow is indeed has polynomial structure, right? So since this flow has polynomial structure, now we use a recent very powerful result given by Siqi Liu, Zhe Wang, and Eugene Zhang. So they said for any bihamiltonian system, if you consider a flow of this Hamiltonian system and using this flow as the space derivative, okay? So this flow is a polynomial is a flow which has polynomiality in the KDD hierarchy, and then you use this flow as space, as a new space variable, and then you can write down the hierarchy again using the new space variable, which is this flow, okay? And then they prove that this after this transformation, the hierarchy is again bi-Hamiltonian. So it's a very powerful result. It's called linear reciprocal transformation because previously there are several types of reciprocal transformations, and this one is called space-time exchange. So it's a particular reciprocal transformation called linear or called space-time exchange. And because of this, we know that this after this change, this what we have using capital X as the spatial variable, you again obtain a bi-Hamiltonian inverse system. And then finally we find that this capital U phi, the relation between capital U phi and U in the KDD hierarchy is a Miura type transformation. And Miura type transformation keep bi-Hamiltonian structure. So this proves that the mapping, WK mapping hierarchy is a bi-Hamiltonian inverse system. Okay, so now I will do some generalization. We will generalize this consideration to the Hodge hierarchy. In this case, we will consider the Hodge bundle of the Riemann-Manford moduli spaces. And
I have a question. It's because Liu Qingzhang and his group, Liu Siqiliu, so they have a classification server for the bi-Hamiltonian structure.
yes,
Yeah. So.
yes, this is precisely what I want to. But before presenting that classification, I will do first a generalization. I will go to that very soon.
And then you try to prove a result says the group action is transitive or something. You change from one.
Yes, yes, more or less we want to yes lift this. Yes, the work is essentially to lift this group action on in that classification of inverse systems. But we need to find that inverse system is very big. We need to find the group action on a smaller subset, and this is what I will explain, the subset. Yeah, and right, it's a very nice question. Thank you. So now we first go to a very easy, very natural generalization. This natural generalization is we consider instead of the Witten-Kontsevich partition function, we consider another set of infinite many parameters called the Hodge parameters. And in these parameters, we will track also the components of Chen character of the Hodge vector bundle. And we get a big generating function. It's called the Hodge partition function. And the logarithm of this Hodge partition function is called Hodge free energy. And several...
Whether sigmas here are just formal parameters?
Sigma.
Sigma.
Yes, we consider sigma as formal variables. Behind it, there is also polynomial structure for sigma. Yeah, it's very also a nice question because we always want to consider if any formal variable can be analytic, but this we haven't done yet. So here we have this another partition function called the Hodge partition function. And several years ago, with Boris Dubrovin, Siqiliu, and Professor Zhang, we gave a construction using, again, Dubrovin-Zhang's formalism, construction of this system associated to any Hodge partition function. And for that one, I will say later. But here we do the direct natural generalization, is that we can also consider the right group action on the Hodge partition function. And then we define deformed Hodge partition function. So it means now we have not just one set of parameters compared to today's work, phi, but also another set of parameters, new parameters, sigmas. Or compared with several years ago's work about Hodge hierarchy, we have again a new set of parameters. So our partition function now has two set of parameters. One is sigma, one is phi. So this makes the consideration more general. Okay, and similarly, this mapping Hodge free energy also has genus expansion, and because the Hodge free energy, the genus zero part, equals the Witten-Conservich free energy. So if the group action make this genus zero Witten-Conservich free energy G invariant, this Hodge is genus zero free energy is also G invariant. Okay. Okay. So here again we want to look at higher genus. In higher genus, with Professor Zhang Dubrovin and Siqi Liu, we proved this Hodge free energy also has this 3G minus 2 jet representation. So here there's the polynomial dependence in sigma, okay? And in this, so when we do the group action, after the group action similar as before, we again obtain this jet representation, okay? For example, in genus 1, now previously we have this term, now we have a new term. This term is sigma 1 over 24 phi v. Okay, this sigma is this Hodge parameters. So, and then for any genus bigger than or equal to 2, this Hodge free energy, genus G Hodge free energy is also has this jet representation. It depends on sigma and also depends on phi. Yeah. Okay, so again, we use Dubrovin-Zhang's formalism, Dubrovin-Zhang approach to get the interval hierarchy. In this case, everything is the same as before. We get a deformation of the local Riemann-Hopf hierarchy. In this case, you see, previously we already have phi, but now we also have a new term, sigma, right? So this is up to genus, up to epsilon square. Okay, so then our result says this local Hodge mapping hierarchy is also has polynomiality, meaning it is also integrable. And in this case, we will give a proof which is a new proof. This proof is for essentially, later we will see it's actually for Hamiltonian case. And in that case, without our approach, still there's not yet a proof. So this proof is a first proof. So let's, again, when phi equals identity, this is known. So it's by the work of Buryak, Potsuma, Chaudhry. So they prove that when phi equals identity, because this Hodge theory is particular cohomology field theory, so then we can use the work of Buryak, Potsuma, Chaudhry to get this polynomiality. And now, again, for the after the group action, we see that again this flow dx is this the same function, right? This flow parameterized by a function. This function is again the same. So for this flow parameterized by functions, actually also appeared in very earlier work in 2000, beginning of 2000 by Boris by Dubrovin. Okay, what he used is called D operators. Yeah, but here is yeah. Okay, and now we consider this tau structure for the for the deformed Hodge theory. For the deformed Hodge theory, the tau structure is the infinite sum of the original tau structure for the Hodge theory. Okay, and this time, since we do not have linear, so is the idea behind is still linear reciprocal transformation, but we do not have we don't know anything about this space-time exchange for Hamiltonian case. So in this case, what we do is that we consider an iteration of this integral PDE, and for a single equation, after the iteration, the polynomiality becomes polynomiality. For single equation, it's always true. And then what we do is substitute this single equation to this original Hodge structure. We will get polynomiality because the single equation has this polynomiality. So after substituting that, this again has polynomiality. Okay, because here is polynomials of wx, double x, and so on. Okay, so this particularly implies when you take ij equals 0, it particularly implies u has polynomiality. U has polynomiality means this u is a Murat type transformation. And because of that, when you substitute, you get a polynomial hierarchy. So in this way, we proved this mapping Hodge hierarchy is also integrable. So here you see it's very important that this tau structure plays a role. Okay, so now let's also write down the Hamiltonian form of this local Hodge mapping hierarchy. And in this case, we only have one survivable Hamiltonian operator. We check up to epsilon 8. The Hamiltonian structure is also polynomial, but we haven't proved this yet. So we conjecture is true for all orders. Okay, so now let's go to the axiomatic way to look at this, to see where this integral system what was there. So it's to answer also Professor Fan's question. So around 2013 to 2016, we proposed two universality conjectures about classification of 1+1 dimensional integral PDEs with one component. So the first universality conjecture says the cubic Hodge hierarchy of a point with the Calabi-Yau condition and with two equal parameters in the term polynomial is the universal object for all tau-symmetric bihamiltonian perturbations of the Riemann-Hopf hierarchy. And the second universality conjecture says the Hodge hierarchy of a point is the universal object in all tau-symmetric Hamiltonian perturbations of the Riemann-Hopf hierarchy. So both of these conjectures are still open. The existence is known. Both existence are known, and actually the existence is given in a better form later by Buryak, Guerri, Rossi, and Dubrovin. But the uniqueness is the difficult part of these two conjectures. Okay, so here the important thing is that we consider intersystems with Hamiltonian or bihamiltonian structure, but we also require the Hamiltonian densities to be tau symmetric. So what we do now is that we want to give a weaker form of the tau symmetry property. Namely, so we will consider Hamiltonian or bihamiltonian perturbations possessing a tau structure, but we do not require this Hamiltonian density to be tau symmetric. So what do we mean a tau structure? A tau structure is a family of omegas, some differential polynomials, such that it satisfies certain property and is also non-degenerate. Okay, and we showed that the existence of tau structure implies integrability. Okay, so and also it's easy to see that the class of Hamiltonian or bihamiltonian perturbations of the Riemann-Hopf hierarchy possessing a tau structure is invariant under the Murat type transformations. Okay, so it means we can study classification of all these perturbations. Right, so the difference with previous work is that we do not require this tau structure comes from the Hamiltonian densities. Okay, and let's do it now. We consider all Hamiltonian perturbations of the local Riemann-Hopf hierarchy, and with the dispersion limit is the hydrodynamic Hamiltonian operator. And so according to Dubrovin Zhang, and independently by De Giovanni, Magri, Shaka, and Getzler, the Dabu theorem holds for Hamiltonian operators of of this form. This form is the perturbation of Hamiltonian operators of hydrodynamic type. So for this case, it means you can find the Muller type transformation reduce all the perturbations. So there are many terms. So here I only gave the leading term. There are many terms, but we can always reduce it to D. Okay. So according to Novikov, Dubrovin, this part gives a flat metric. So this GU, if you want to make it to be 1, is just by finding the flat coordinate. Okay. So and then this W theorem generalized the G 0 to all the dispersive operators. So, and Siqi Liu and Youjin Zhang, they found that performing a canonical Muller type transformation gives rise to the so-called unique standard form of this classification, which means that now our Hamiltonian operator fixed is just D, but we can also have canonical Muller type transformation, which is a Muller type transformation keep this D invariant. So it's like canonical variables. So when we do this, we can make the Hamiltonian density to be this unique standard form. Okay. Okay. So this standard form is characterized by certain arbitrary functions, A0 and alpha lambda. These alpha lambda are labeled by partitions. Okay. So Liu Zhang conjectured that if the standard form is integrable, then each alpha lambda is uniquely determined by alpha to the n, so by some particular partitions, and also so this alpha 2 to the n are free. Okay, so in our work we also show that if we impose this Hamiltonian density to be tau symmetric, then all these parameters becomes constants. But on the other hand, there is another classification work by Dubrovin to consider bi-Hamiltonian perturbations. So in this case, Dubrovin shows in 2006 that if there exists a Poisson operator or Hamiltonian operator P2 such that this hierarchy Poisson commute up to epsilon 6, then alpha 2 to the 2 is given by is uniquely determined by A0 and Q, okay, this metric. And we also compute, following Dubrovin, we also compute the central invariant of this Poisson tensor. Okay, it's given by this expression. So now we have essentially two functions. One is A0, one is Q. Okay, so what we do is that we consider this bi-Hamiltonian system, and also we consider it has, we require it to have a tau structure. Then our classification work, we find that in this case, alpha 2 to the 2, instead of it is given by this, in this here, Q is more or less free. It's a free function, always flat. So Q is free, but here, alpha 2 to the 2 is no longer free. So it's different from, it's a special case of Boris construction. Actually, we have, let's say this one is integrable. This one is bi-Hamiltonian, is what Boris was trying to do. And here we also have another one's tau structure. And what we do is here. And actually this is tau symmetric. Okay, so in this case we find that for this 2 to the 2, 2 to the 3, 2 to the, here is 2 to the 4. In each case, we have a free parameter Q1, here Q2, and Q3, and so on. So for tau symmetric case, for this classification, this tau symmetric case is the case when A0 is a constant. In this case, you see all this disappear, only survive this, and this. This is the Hodge case. So now you have an arbitrary free function. This free function A0 will correspond to our group element phi. Is the main conjecture later. So when we perform the bi-Hamiltonian test for this, excuse me, sorry, excuse me, sorry, here in this classification, we haven't put bi-Hamiltonian with Hamiltonian plus tau structure. But since tau structure implies integrability, so it is integrable. So in this case, sorry, I slightly say something wrong, but here is Hamiltonian plus tau structure gives this picture. It's more general than Hodge. Okay, and now we give this bi-Hamiltonian test. I should draw a very clear picture, but maybe I will do later. So in this case, what we found is that this Q2 is determined by Q1, and Q3 also determined by Q1 because 0, and Q4 determined by Q1, Q5 is determined by Q1. And we get a sequence of very interesting numbers, and this sequence of numbers has topological meaning. So it's something we will do, find the pattern later. And so we also show that this central invariant in this case is 1 over a affine linear function. To answer Professor Fan's question is that what we have is in the previous work of Liu, Zhang, and Dubrovin about bi-Hamiltonian system, we now restrict to the case when the central invariant is 1 over a affine linear function. And also there is a Mobius transformation behind the central invariant. If you use the Mobius transformation, essentially we will get its constant central invariant. So this is essential what we do. So now let's look at the main conjectures. First is WK mapping universality conjecture. This conjecture said the mapping hierarchy is the universal object for all bi-Hamiltonian perturbations with a tau structure. And we also have this Hodge mapping universality conjecture. The Hodge mapping hierarchy is the universal object for all Hamiltonian perturbations with the tau structure. So generalizing the previous universality conjectures. We also gave a direct verification of these two universality conjectures up to epsilon 8, which means we can map the standard form to the to these mapping hierarchies. Okay. We also gave for Hodge mapping hierarchy some direct verification. Okay. So. Time is on. Maybe I will speak very quickly the second application of this work. Yeah. So the second application, we want to do something about partition functions. So it's also go back to the particular example of Alexandrov. So the particular example, you see, if we consider phi equals this starts with V. Okay, so it is a particular element in the group. In this case, the ground ring is the ring of polynomials of Q. Okay, and in this case, what we obtain is an accurate identity between a particular cohomology field theory and the Witten-Kontsevich partition function. Okay, and this particular cohomology field theory is given in terms of the Chern class, a Chern polynomial of the moduli space in this particular form. And so we call this identity the Hodge WK correspondence. And this result was actually essentially first obtained by Alexandrov with a different proof. And before his Alexandrov paper on archive, we also found by ourselves two other proofs. And the proof given finally in our paper is another proof. So now there are in total 4 proofs. Okay, so in 1990, Witten proposed 2 kinds of quantum gravities: topological gravity and matrix gravity. Topological gravity is what we see many times in this conference, is this Witten-Kontsevich partition function. So in around 2016, with Dubrovin and Liu and Professor Zhang, we gave a Hodge GUE correspondence. In this correspondence, we gave a relationship between this particular cohomology field theory with the matrix gravity of Witten. And recently, we also gave a relationship between this particular cohomology field theory with Qingsheng Zhang with the generalized Brisson-Gross-Witten model. Okay. So now, since we have Hodge GUE, a cohomology field theory with matrix gravity, we also have a cohomology field theory with topological gravity. But this one, the new one, is invertible. So which means if this is invertible, you can make Hodge as the middle, and you can give a relation between WK to GUE. Just one of these correspondences is invertible. You can make a new correspondence, which we call WK GUE correspondence. And this correspondence gave, I think, the first accurate identification between these two quantum gravities. So it's written in this theorem. The left-hand side is the Witten-Kontsevich partition function. The right-hand side is the matrix gravity suggested by Witten. So finally, these two gravities are equal. So it's after many years work, we finally made it. Okay, so, and also again, since this is invertible, you can also get a relationship between Witten-Kontsevich and generalized BHW. So you see this relationship, the time change here is quite non-trivial because it is a composition of a non-invertible map, linear map, affine linear map with an invertible one. After the composition, it becomes this form. So here you have the generalized BGW, and the times are called R. And you make this, in this case, it's not triangular, but anymore, it's not triangular anymore. But you make this transformation in the Witten-Kontsevich partition function, you make them identical. So I will stop here. Thank you.
Please, any questions?
Whether your results allow one to compute explicitly Hodge integrals, for example?
For Hodge integrals, yes. We have an algorithm to compute the Hodge integrals.
Not necessarily linear Hodge integrals.
Yes, for arbitrary Hodge integrals, we have an algorithm. So yeah, but that algorithm was based on Faber-Panhard-Pound equation.
Any questions?
Can you say it again? Why do you say that this topological gravity identification with matrix gravity?
Yes, so Witten proposed two partition functions in the study of two-dimensional quantum gravity. One is the generating series of psi-class integrals. The other is the generating series of ribbon graphs, counting ribbon graphs. So, and these two, so...
You had a counting problem for polygons.
Yes. So it's a dual graph of ribbon graph is the polygons. Yeah, but many people think the two gravities has some equivalence, but there's not yet any accurate relationship. But now this is the accurate relation between these two gravities.
You say that there was no such.
Before there's no such quantitative precise relation. In the big fish space.
But there was some argument.
There was some argument.
Not very rigorous.
There are some arguments if you go to the jet space, there's some known identification, but not in the big fish space. That one can be rigorous, but in that case already, since you use the jet variables, it's not direct connect to these correlators. Yeah.
written conjecture. Can you write down the
You're right. So not yet. So we want to generalize to any n-dimensional calibrated semi-simple Fermi manifold. In this case, the group will be affine linear transformations whose linear part is close to the identity, so that is invertible, such that the general zero free energy is invariant. But we haven't found out for our spin case, for example, how the group. What I guess this group will not be so. Riemann's group is very nice, but in this case it will be similar to Riemann's group, but it's more. It's because Riemann's group looks like a little bit easy, but here it should be some already non-trivial when the dimension of the Fermi manifold increase.
Could you comment on this ramification mapping?
Not yet. I haven't tried to compute. Yeah.
Okay. But what you mean is that you expect to find a transformation phi which maps the.
So here it's the comment is very easy. So we do the same thing for the double ramification partition function. And then what I expect is that for example, for the rank 1 cohomology field theory, if you do this, you will get something still polynomial, and it would be nice if it is directly the standard form, like in the Hodge case, when the group is when the group element is identity. But as kind of we can believe it will be nice. I mean, the double ramification will be nice.
I think now let's thank the speaker. And we have a lunch break till 14:50.
Can we leave it here? Better not.
Yeah, I think we can leave it together.
Yeah, but okay.
Yeah, I think it's safe. I mean, that it cannot be all of us like can drink here, of course. What is announcement that, yeah, I suggest to go for lunch outside now.
Outside, not the
Yeah, there's the weather is nice and there's a nice place outside. And also, yeah, one more remark. Today and also tomorrow we can't cover lunches, so paid by participants.
Partition function of Hodge integral.